So in 6.5 and 6.6, we're basically going to be applying the central limit theorem and checking normality. Specifically in 6.5, this is kind of where we left off, that for the central limit theorem, any population with mean, mu, standard deviation of sigma, we saw that the mean of the means equal the true mean. Standard deviation of the means is sigma over square root of n. I'm going to have a whole separate project on this in class, so don't stress too much about that. But I'm going to actually show this to you, so but you should already have that copied down. How do we apply this? Well, here's an example if I was talking about the weight of men. Okay, so if the weight of men had a mean of 182 pounds and a standard deviation of 40.8, right? That means that the individual average is 182.9, standard deviation of 40.8. If I were to go one standard deviation above, this would be the 182.9 plus the standard deviation of 40.8 gives us 223.7, right? And if I went one standard deviation down, this would be the 182.9 minus 40.8 to give us that 142.1. So this would be one standard deviation above, one standard deviation below. This would be the population distribution right here. How would a sampling distribution, if I were to sample 100 men and collect their means, collect their average weight, not of the individuals, but of the 100 men, okay, and I made a collection of those data points? Well, I would expect the mean of the means, the mean of all those different groups I took of 100 men, if I took the average of those 100 men, the average of those should equal the true mean. The mean of the means should equal the true mean, right? But the standard deviation of those means will not be the same. We said groups deviate less than individuals. So specifically, what the central limit theorem says is that this will be sigma divided by square root of n, or the true standard deviation, 40.8, divided by the square root of, what was the sample size? Well, we sampled 100 men, so we would be divided by the square root of 100. And that would be 4.8. What would that do to my distribution? Well, 182.9, the next number would not be 223. It would be, what would it be, 187.7. How the heck did I get that? Well, it would be the mean plus our standard deviation. And this, once again, would not be 142.1. It would be 178.1. That would be the mean minus one standard deviation. The sampling distribution would deviate much less than the individuals in the population distribution. The sampling distribution is actually much more narrow. There is less deviation in groups than there are with individuals. Now be careful. This is only true if the population is already normal, then done. We will have a normal distribution. A bell shape follows. We can use the empirical rule. We could check the probability plot. We have normality. Okay, central limit theorem will work. If the population is not normal, we need to sample at least 30 people, greater than or equal to 30. And what that does is we get normality. Once again, I'm going to have a whole project on this to kind of show this, because it's important that we know when we have normality. What it also does is it changes our formula, and this is what we're going to be using in section 6.5, is it changes our formula for z. Because the z-score for a sampling distribution, remember, I'm not looking at an individual x, I'm looking at a mean here. So the probability that a mean equals a number will be that score, instead of x minus mu over sigma, that was kind of our old z formula, okay? It's going to be x bar, because we're not dealing with an individual, we're finding the probability of an average, okay? So it will be x bar minus mu, because the mean of the means equals the same, divided by, this not just sigma, but divided by sigma over square root of n, okay? So we have a new formula for z when I'm finding the probability for a sampling distribution, okay? If we don't know normality or the sample size is less than 30, then we cannot use the central limit theorem. We will not have accurate results, and so we don't do it. All right, so that's kind of my little preview of what we need to know, and now we're going to apply it in this little worksheet, okay? So I'm going to recap. I'm a little different than this book because they say greater than 30. That's where they draw the line. Kind of heard it both ways. Fine, greater than 30 is what they're going to want in your homework. So we can do that. The sampling means have a distribution that's approximately normal, with the mean of the means equal to mean, and the standard deviation is sigma over square root of n. If it's less than or equal to 30, and the population is normal, then the sample mean will be normally, so it still works as long as the original population is normal. And if it's less than 30 and it's not normal, central limit theorem does not apply. Okay? Some notation. Mu is our population mean. Mu of x bar is the mean of all the means. So the mean of the means is how I refer to it. I actually like this. It's a nice little approximation of the central limit theorem. The mean is equal to the mean of the means. Sigma is the population standard deviation, sigma of x bar, and the sigma of x bar will be the true standard deviation divided by the square root of n. Let's apply it. Assume that women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5. If one woman is selected at random, find the probability her height is between 60 and 65 inches. Okay? This is actually not a 6-5 question. This is a 6-3 question. You're like, well, how am I supposed to know the difference? Well, we are dealing with an individual. See, in 6-5, we're doing the probability of groups. This is saying the probability of one person of X is between 60 and 65. So I need to actually put that between 60 and 65. Okay, we've done this already. This is going to be norm CDF min, I missed the C on there, sorry, min, max, mean, standard deviation. So norm CDF, our minimum is 60, our maximum is 65, our mean they gave to us was 63.6, and our standard deviation was 2.5. So this is not new. Let me get a calculator page here. So menu, out of there, menu, statistics, distributions, norm CDF. We are going from 60 to 65. These are not z-scores, so we need to fill in the mean and the standard deviation. So I'll need to fill those numbers real quick. 63.6 and 2.5. So 63.6 and 2.5. So there is a 0.637, there's 63.7% chance. A 63.7% chance of an individual woman having a height between 60 and 65 inches. Height of 60 to 65 inches. Okay? Does the central limit theorem apply? Well, the sample size is 25, so my temptation is to say, nope, 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 nope. They said more than 30. So we're done with this question, right? Well, no, we said the central limit theorem works if we have more than 30, or if we know the population is normally distributed. Do we know the population is normally distributed? Somebody's like, yeah, well, look at your screen. It says we know that women's heights, or we're assuming that women's heights are normally distributed. We actually know that. If we were to map out all of the heights of the women in the population, we know that we're dealing with a normal distribution. Okay? So we know that, does essential limit theorem apply? Yes. Why? The population is already normal. So what the heck does that do for us? We now can ask a 6-5 question. What the 6-5 question says, what if I were to sample 25 women and I were to collect their average height? What's the probability that their height would be between 60 and 65? Now keep in mind, this is not an X. Yeah, it is. You just wrote an X. No. They want the probability that the mean height of those 25 women is between 60 and 65. This is an X bar. This was an individual woman. This is a group. The probability that that group will have an average height between 60 and 65 inches. How does this change things? Well, we still use norm CDF. Because it's normal, we can still use this normal distribution. We will still have the same min, the same max. What will the mean of the sampling distribution be? Well, by the central limit theorem, it's equal to the true mean still. What will the standard deviation of the sampling distribution be? It will not be the same. It will be sigma over square root of n. Why? Because we expect the group to deviate less than the individual. So I would put in norm CDF 60, 65. The mean of our population is still the mean of the means, and the standard deviation is not going to be 2.5. It will be 2.5 divided by the square root of n, which is 25 women. We sampled 25 women. So 2.5 divided by 5 will be 0.5. Those will be the numbers we put in. Notice that the sample of 25 women deviate less than the group. So I'm going to go run this again. Menu, statistics, distributions, norm CDF from 60 to 65, same average, same, what was it, 63.6, I think? Yep. Doubted myself. And standard deviation. Technically, you could put the whole formula in here, but we already calculated it, so I'm just going to put the 0.5. I'm pretty sure they'll let you put the formula in there. And I'm actually worried that I just did that right now. I'm thinking about it. No, I'm good with that, 0.5. Okay, but the square root of, I'm sorry, what was it? 220, what was it? Yeah, divided by the square root of 25. It may freak out, we'll see. Yeah, it doesn't like that. So yeah, the 5 didn't quite get in there right. Technically, I could put the formula in there, and that. All right, technically I'm tired of this, so let's just make that 0.5. 0.997. That is a much higher probability, right? Because we're not dealing with individuals, we're dealing with a group. So 0.997, let me write that down. Maybe. There is a 99.7% chance that, not an individual, a group of 25 women will have an average height between 60 and 65 inches. What might help with this is if we kind of draw it out real quick. So basically, just a quick recap, this on A represents our actual population distribution with a mean of 63.6, and every standard deviation is 2.5. So it would be 65, 66.1, 68.6. We're going up by 2.5, right? This would be 61.1, and I don't know, a little more complicated, but it's going up and down by 2.5. Down here represents a sampling distribution, because I'm not dealing with individuals, I'm dealing with a sample. The mean will still be 63.6, but instead of going up by 2.5, we go up by 0.5. So it'd be 64.1, 64.6, 63.1, 62.6. See, so if I was going to shade this, and I'll just kind of do an approximation here, but between 60 and 65 here is going to be like 60 to about 65, right? So that's just that's a pretty good chunk. That's about 63%, right? But if I do this between 60 and 65, I haven't even reached 60. 60 is like way back here, and 65 is almost all the way over here, right? So we've almost shaded dang near the whole thing. In fact, 99.7% of it. We've shaded nearly all of the distribution because the standard deviation was much less. Particular hotel, guests spend an average of 11.4 minutes in the shower. Assume the shower times are normally distributed with the standard deviation. Find the percentage of guests who shower more than 12 minutes. We are dealing with, in A, the percentage of individual guests. What's the probability that an individual guest showers more than 12 minutes, right? So let's look at this and go, okay. So the probability of an individual being greater than 12. Norm CDF. Our minimum is 12. We're going forever to the right, so infinity. Our mean and our standard deviation. Done. I think we have a calculator for that. Norm CDF. We were going from 12 to infinity with a mean of 11.4, then 2.6. Okay? So about 40.8%, 40.9%, 0.409. So about 40% of people shower more than 12 minutes. Okay? The hotel has a system that provides enough water so that if the average is less than 12 minutes, right, then we are going to have enough water. So if the average is more than 12 minutes, we don't have enough hot water. We have angry people, right? So if the hotel currently has 84 guests, should we worry that we're not going to have enough water? Well, you're like, yeah, look, 40% of the people are going to use too much water. So 40% of the people use too much water, we're running out of water. Is that what this says? Well, not exactly, because this didn't say that each guest has to spend less than 12 minutes. They said 84 guests need to have an average or mean shower time less than 12. This is a different question. This is saying, well, what's the probability that there's not enough hot water? Well, that's if the average of 84 guests is more than 12. Then we run out of hot water, right? How does that change this? Norm CDF. Keep in mind again, this was a 6.3 question. This is now a 6.5 question. Our minimum is still 12. Our maximum, our mean didn't change, but our standard deviation is no longer 2.6. It's 2.6 divided by the square root of 84. So 2.6 divided by the square root of 84. So 0.2836. I'll just do 284. I'll keep it in the calculator. So what I can do now is I can just rerun this. And rather than go all the way through the whole calculator again, I'm just going to go back up to this, seal it, and then in place of the 2.6, I'm going to put 0.283683. And I'm going to put as many decimals as I can to keep this as exact as possible, because the computer will penalize you for not being exact enough. So 0.017. Am I worried about running out of hot water? Well, even though 40% of the people are going to use too much water, there's less than a 2% chance of us running out of water, because the average of the 84 people won't be more than 12. Well, there's about a 2% chance. Am I freaking out about running out of water? Is it effective? Now, this is your opinion. You may go, yeah, 2%, we're going to be fine, right? Out of every 100 days, out of every, 3.5 months, we're going to have 2 days of water we run out of. Some of you are going, I don't think that's a good business model, because we've got Yelp, we've got all these people that I don't even know what they use anymore, but they're going to assess how good our hotel was, and those 2 days, every 3.5 months, I'm going to have 2 days that people just put my business on blast, saying, your business sucks. I tried to get a hot shower and the water ran out, right? So does the current system appear to be effective? Yeah, 2% is pretty low. But if you're a business person, you go, you know what? I don't want the bad reviews. I don't even want that to be 1%. I want that less than 1%. I want this to maybe happen once a year at most. Okay, so that last question is really kind of up to you. Last one, and I love this example. Okay, I love this example illustrating the central limit theorem and the power of our statistics. Okay, the idea of insurance is that we all face risks. They're unlikely, but they carry a high cost. Think if a fire destroys your home. So we form a group, share the risk. We all pay a small amount. Okay. Insurance company looks at the records, 4 million homeowners, and says, the average loss is $250 per house. You're like, yeah, it's not too bad, but keep in mind that's over millions of people, right? Some people have great losses, some people have no loss. And the standard deviation of that is about $1,000. Okay? If the company sells 1,000 policies, will the probability of the average loss be greater than 275? Or what is the probability, right? So this is saying the probability that, not that the individuals, but that on average, my 1,000 policies, right, have a loss greater than 275. Can I use the central limit theorem? Do we know that this is normal? In fact, they said no, it's extremely right skewed, right? So does that mean, I can't use central limit theorem? No, what's our sample size? Even though it's not normal, our sample was 1,000 people. That is definitely enough for the central limit theorem to kick in. We said we wanted at least 30. 1,000 is at least 30, right? So because it's normal, I can use norm CDF. What's my minimum? My maximum? Well, you can go up to really expensive houses, right? What's our mean? What's our standard deviation? It's not going to be 1,000, right? It's going to be, so what is 1,000 divided by the square root of 1,000? I don't know. What is 1,000 divided by the square root of 1,000? Well, that's not helpful. How about 31.62? So what we're going to do is find this probability, okay? So norm CDF, we said 275 to Beverly Hills prices of homes. The mean, we said was, make sure I'm doing this right, 250. And the standard deviation, we approximated, I probably should have written some more decimals down, was about 31.62. And but actually, before I hit enter, I might just add some more decimals to that. I could put 228, see if it makes much of a difference. What if I made it 228? Pretty good. We're not going to have any issues with 3 to 4 decimal places on that. So 0.215. So what are we doing here, right? Well, I'm going to sell fire insurance for $250 plus that's $25 to cover costs and profit. I want to make money on this, right? So if I'm selling for $275, I'm selling you an insurance policy on your home. Am I making money? Well, as long as, right, the people actually claim less than $275, I'm making money. Well, this says, what's the probability that I lose money? Because if I have claims greater than $275 and I'm only bringing in $275, I'm broke, right? So there is a 21% chance that at the end of the year I lose money with this company. Is this a good business model? Right? 1 out of every 5 years I'm losing money. Probably not the way I want to run an insurance company, right? So what are my options? And here generally I have people go, well, let's just raise the price. Let's go, you know what, $275 isn't enough. Let's say, you know what if we make it, instead of charging $275, I'm going to charge $300. Well, now there's a 5% chance. So 1 out of every 20 years. That's looking better, right? You're like, well, I'd rather that be close to like 1%. So maybe we charge $350. I'm liking those odds. But what's the problem? If I start raising rates on people, I'm having a harder time keeping people signing up for my company, right? So yes, I can raise the rates, but then people go, nah, I'm going to go switch to Mutual or this Lizard guy, and I'm going to basically save money because you're charging too much for my fire insurance policy, right? So what if, instead of selling 1,000 policies, we just sold 10,000 policies? You're like, that sounds like we took a bad thing and we made it 10 times bigger, right? If that's what you're thinking, then you don't understand the idea of statistics yet and the power of the central limit theorem. See, what if I said, let's not raise the price. I want you all to go out and sell. Sorry, I'm not raising the price to $275. I want you to sell 10,000 policies instead of 1,000 policies. Let's double down on this effort 10 times, right? So what's going to happen here is norm CDF, same price, $275. Infinity, 250 still the mean. The standard deviation is now different, isn't it? It ends up being 1,000 divided by the square root of 10,000, which I think is just 100. No, it should be just 10. Sorry. Keep me honest there. Well, we have less deviation now, right? So how's that going to change our model here? Well, let's see. Change that from that to 1,000 divided by the square root of 10,000 should be 10. So I'm going to just do the same exact thing that I did last time with the, where is it, the 275. But I'm going to change the standard deviation to 10. What happens, right? You're like, I'm going to lose money. You just said I'm going to lose money. And I did 10 times as much. There is now a 0.006% chance of me losing money. What the heck just happened? This is the power of statistics right here. Okay? There is now over here there was a 21.5% chance I lose money. Down here there is a 0.6% chance I lose money. Right? What the heck happened? Well, up here, our average was 250, and each standard deviation was 31. The next one was 281.62. Where's 275? Well, kind of close to the 281. So this was our probability of losing money. What happened down here? Well, the mean's still the same, but the standard deviation is now 10. So here's 260. Past that is 270. Past that is 280. Where's 275? Between 270 and 280, here's my probability of losing money now. Instead of a 20% chance, there's a 0.6% chance of losing money. What did we say, right? Groups deviate less than individuals. You're like, yeah, I know. What does that have to do with this? Well, if groups deviate less than individuals, then the larger the group, the less the deviation. So a larger group deviates less. So I sold more policies and I lowered my risk. In fact, I might lower this from 275 to 270. Take on some more risk so I can sell more policies and cover that risk. So you got to be careful with this. Like I said, kind of the power of statistics. Last thing I want to do is look briefly at 6.6 and just how do we check normality. You will have to be doing this a little bit in the homework, but I have one question where you can use this, but I'm not going to do much with this until actually the later chapters. So briefly, the way that we assess or check normality is we use what's called a normal probability plot. That's a lot more exact than looking at our histograms, and I'll kind of show you that. It's also called a normal quantile plot or a QQ plot. We take every value, every x, we calculated z-score, and we graph the x values versus the z-scores. If it's perfectly normal, you end up with a straight line with 68% of the data being within one standard deviation, 95 being within 2, and pretty much all the values being within 3. But all you're looking for is that when we graph the x's versus the z-scores, I'm looking, ideal means I've got a straight line mostly. Okay? I want there to be no patterns, and I want it to fall mostly normal, mostly kind of randomly around that straight line. When is it not ideal? Well, if I do, and actually I'm going to do random integers, so I'm going to do different here. So I'm going to do random integer between 1 and 100, and I'm going to do 100 numbers. Okay? What's going to happen is you're going to have your perfect line, and the numbers kind of fall away, and then they fall towards it, and then they fall away again. So it's not kind of the numbers falling all normally around the line. You have some kind of curvature. It falls away from the line. Okay? So take a second and kind of sketch those. And what I'm going to do now is we're going to look at some data sets, and we're going to show you how to do this with some data in the calculator. So what I did is I've made a couple distributions. My first one is where I did the command was random normal with a mean of 100, standard deviation of 10, and I did 100 numbers. Okay, so it generates 100 numbers. And I went up here and I named that my normal data, my normal distribution. Okay? So ran norm 100, 10, 100. I got those 100 numbers. If I were to graph those on my normal data, it looks mostly Well, it's like hard to tell, but mostly normal. I could make that into a histogram, and I'd say it's roughly normal. With 100 numbers, it goes to a peak and falls down about evenly. Yes, there's some gaps that happen sometimes, but this is roughly normal. Okay? If I did a normal probability plot, it's not difficult to do. If you have this already, go to plot type. Where do you see a normal probability plot? That's the fourth option. That's it. Notice how the numbers, yes, they fall away a little bit, but they keep kind of falling around this straight line. This would be roughly normal. What if I said, I'm going to create something that's not normal? I want a random integer between 1 and 100. Well, this should fall pretty evenly between 1 and 100. It's not going to like bias itself towards the middle. I'm going to have random numbers between 1 and 100. Okay? When I go to look at that graph, let me go back to just the dot plot on the not normal. This is pretty standard level. This is not normal. If I looked at it, as a histogram, you'd say it's not going to a peak and coming down. This really is not normal. What does it look like as a probability plot? There's where it's curving away. It creates kind of a pattern above, below, and then curving away. This big curving away implies this is not very normal. Okay? The last one, and you can go ahead and do this last one with me. I call this the really not normal. So we're going to make up some numbers that are definitely not normal. So I'm going to say, what if I had a 1, 2 2s, oops, 2 2s, 3 3s, 4 4s. I think you're seeing a pattern here. 5 5s, 6 6s, 7 7s, I don't know, I just lost count. And we'll do just a bunch of 8s. This should not be normal looking. This should be really not normal. Okay? Remember, if you're going to graph it, you have to name it. If I go to this and I change it from, let me change it back to the dot plot just so we can see, to the really not normal, this is not at all normal looking, right? If I look at my histogram, that's not normal. If I look at the normal probability plot, it starts to fall, but then it just gets this like numbers that pull away. This is not normal. So most of them should fall kind of normally around the line. Anything where you have a big cluster falling away implies that it is not normal. So that's how we check normality, is using what's called the normal probability plot. That's all they're going to have you do mostly in that last section, is they're going to give you some pictures and say, is it normal or not? And they're just kind of prepping you because we're going to use that skill in the future chapters. So not too bad. On the test, I think I might have one where I give you a set of data and have you do it to look at it, but mostly I think what I do is I give you a picture and I ask you to decide whether it is normal or not.